Now, when we analyze data, we need some basic analytical measures, especially for continuous data. For categorical data, we'll pretty much use crosstabs, cross-tabulations, tables to determine how many in a particular category we have. If we have two categories, we count them. If we do two variables and two categories, we'll have a 2x2 matrix. But that's not what we're looking at here right now. One of the main concepts is called the measures of central tendency for continuous data. Central tendency is a term that helps us understand a typical or central value for the variable. So some measures of central tendency include the mean, the median, and the mode. Our analysis will require descriptions of data set, and this can also be done using percentiles and quartiles, and we'll see how all of them are related. It is important to understand how the data spreads around the central tendency. Measures of variance and standard deviation are critical to understanding the variability, along with things like skewness and kurtosis. Many of you watching this are probably already familiar with the mean. It is the most commonly used measure of central tendency, especially for a data set that is normally distributed. And it is the average. The average is calculated by adding up all of the values, and that's that sigma I. We add up every single value and divide by the number of values we have. And this gives us the x bar. So just something for notation, if we're using Latin letters like x, that's basically the sample statistic that we're looking for. So in this case, it's the sample mean. If we're looking for a population mean, that's going to be represented by the Greek letter mu. So when we refer to measures that are from a sample, we're going to use Latin letters, and when we refer to population statistics, we're going to be using Greek letters. So if we're going to do the mean in R, we're going to use the function mean, M-E-A-N, and we're going to pass in some data. The na.rm equals false would basically leave any missing values. And so generally you might want to do na.rm equals true to remove missing values. The median of a variable in a data set is the center or middle of the data. So given a set of numbers, 1, 4, 5, 3, 4, 11, 4, 1, 2, we would first need to order the set to be 1, 1, 2, 3, 4, 4, 4, 5, and 11. Since there are 9 numbers, we take the fifth number, which in this case is 4. Now, if we have an even set of numbers in the data set, we simply average the two middle numbers. So consider we have 1, 1, 2, 3, 4, 5, 8, 9, 11, and 12. We'll take the middle two numbers, which are 4 and 5, and the median will be the average of the two, which is 4.5. In R, we have the function median. We pass in the data column or the data set, and it will provide the median of that data set. Again, you have the na.rm option as well. Set it to true, and it will remove any missing values. So the median has very good properties, especially when the data set is not normally distributed. So if you take a course on the theoretical distributions, you're most likely going to look at the median. And the reason why is because the median represents the 50th percentile. 50% of the data fall below the median, and 50% of the data falls above the median. The normal distribution, in the normal distribution, the mean and the median are theoretically the same, which is one of the reasons why the average or the mean is so widely used, because data in many cases is normally distributed or considered to be normally distributed. And so therefore there's no distinction between the mean and the median, or that they're very close to each other. However, in other distributions, that's not the case, such as the exponential distribution or the Poisson distribution. Now, a third measure of central tendency is the mode. The mode of a variable is the most frequent number appearing in the data set. Given a set of numbers 1, 4, 5, 3, 4, 11, 4, 1, the most frequent number in this data set is 4, and so therefore the mode is 4. If two numbers appear the most times in a data set, such as in this data set the numbers 4 and 1 appear most frequently, we say that the data set is called bimodal. If we have more than two modes, then it's going to be known as multimodal. Now, R doesn't provide a mode function by default, but a few packages have the mode built in. And what we've done is we've provided a mode function for you here at the blog's 5eanalytics.com in the R code library. Now, quartiles are useful to help split the data set, to understand how it can be distributed. Since we know the median is the middle of the data set, 50% of the data fall below it, and 50% of the data falls above the median. We can use this concept to help us understand quartiles. So consider if we split the bottom 50 in half and the top 50% in half, we would now have 4 equal parts. Thus, these 4 parts provide the quartiles. So the first quartile is the lowest 25%. The second quartile would be the second 25%, which is the section just below the median. The third quartile is the third 25%, which is just above the median. And the fourth quartile is the remaining, or the highest 25%. In R, we can obtain quartiles by using the quantile function. Now, we'll take a look at that in a second. But with the quantile function, we'll pass in the data, and we will tell it which quantiles or which percentiles we want. So the quartiles would be the 0.25, the 0.50, 0.75. So graphically, this looks like this on a box and whisker plot. The first quartile is all the way to the left in the first whisker on the left side. The IQR, or interquartile range, represents quartile 2 and quartile 3. The median is represented by that thick line in between the two quartiles of 2 and 3. And the whisker to the right is the fourth quartile. So this gives us not necessarily 4 equal quartiles, but it basically tells us how the data is spread around its particular median. Now with a percentile, while it's more appropriate to say that quartiles are representations of percentiles, it's a bit easier, in my opinion, to consider the reverse, that percentiles are an easier way to consider quartiles. The quartile ranges represent respective percentiles, 25%, 75%, and 50%, as an example. So therefore, when we state an X percentile, we want to know the observations that fall below that X percent. The 33rd percentile, therefore, is the point at which 33% of the data falls below it. And if we had the 72nd percentile, it would be 72% of the data falls below that percentile. Percentiles in R are obtained by using the quantile function, as we had talked about earlier. So here's an example. Quantile, first parameter will be the data set. Then we will pass a vector of the percentiles that we want. In this case, we want the 33rd percentile and the 72nd percentile. So it will give us the values at which 33% of the data falls below it and 72% of the data falls below. You can use these for quartiles by simply changing this to 0.25, 0.50, 0.75. You can also add a 1 at the end for the maximum as well. Now, the most important concept in statistics is the variance. The variance of a data set or variable measures the spread of the data around the mean. It's a great way to understand how far or near the data is to its measure of central tendency. Let's say we have a set of numbers, 1, 10, 50, 75, etc. And another data set, 1, 2, 2, 7, etc. It's clear to see that the first data set has a very wide dispersion, while the dispersion in the second set is much more narrow. So this gives us a way to talk about these particular data sets. Consider this other example. Let's say we have a data set that has a mean of 500, but the numbers range from 1 to 1,000, 20 numbers that range from 1 to 1,000. Let's take another data set with a mean of 500 as well, but the range only goes from 490 to 510. The two data sets are clearly different, even though they have the same mean. So it's important to understand that spread because it will be indicative of how that data actually operates and where other data points might fall in. Now, the population variance is denoted by sigma squared, and the sample variance is denoted by s squared. Again, the Greek letter is used for the population, and the Latin letter is used for the sample. So we have the following formula for the variance. We'll focus on the sample side. We'll take each observation, which is xi, and we'll subtract x bar, which is the mean of the sample. Taking this piece alone, we can see that this represents a distance between each observation and its mean. So if, for example, we had the observation as 4 with a mean of 10, it would give us a negative 6. And if we had 14, we subtract 10, we would end up with a positive 4. But distances really can't be negative Distances are measured in positive numbers. You're a certain distance away from the mean. So what we do is we can remove the negative by squaring it. Then that -6 from our original example becomes 36. The negative sign has been removed. But the squaring does one additional thing. It penalizes observations that are further away. So the further away you are, the higher that portion, that xi minus x bar squared, will be. Now that's important because if we have a very narrow dispersion where we have something near, a lot of the data points near the mean as an example, you might have, say, again, our x bar is 10, the number 9.5, when we square it, is not going to have a very high value once we square it. But a number, let's say, that's 0 as compared to our x bar being 10, the difference is 10 and we square it, that's 100. So the further away we are from the mean, the more this formula is going to penalize us. So that when we add them all together, we're taking the sum of the squared distance. By dividing it by n or n minus 1, we're computing what would be an average. The reason in the sample that we're taking an n minus 1 is for a correction. The full reason we'll leave for another module in statistics. But for now, if we assume that this was nothing more than just an average, that's what we would end up with. We are taking the average squared distance. The top is representing the squared distance summed, and we are then taking an average. So when we use R to obtain the sample variance, we're going to use the function var in the same way that we did mean and median. We put in a data set where the 3 dots are, and again we can choose na.rm equals to true or false, true being remove any NAs or missing values. Now the standard deviation is much easier to interpret than the variance. The variance is going to give us a number, but it doesn't give us anything that we can necessarily interpret for someone else. And the standard deviation is, while it's nothing more than the square root of the variance, it actually will give us something a little bit more interpretable. It gives us a better measure of the dispersion of the data in the form of a percentage. So for example, 68% of the data will fall between plus or minus 1 standard deviation of the mean. Now this assumes that the data follows a normal distribution. 95% of the data will fall within plus or minus 2 standard deviations of the mean. And 99.7% of the data will fall within plus or minus 3 standard deviations of the mean. And generally, we can see this in this graph. We have a normal distribution here, which is a bell curve with a certain mean. And 1 standard deviation basically gives us 68% of the data within that section. 68% of the data will fall in that blue area. And that's what makes the standard deviation so important and so critical, is because we can use it to identify some of the key factors, some of the key facts about our data.